Now that we have a practical definition of continuity, we're going to do two things in this lecture. First, we're going to look at some properties of continuity here on this slide. And then we're going to look at some specific examples of functions and see how we can use our definition of continuity to determine when and where a function is continuous. So we have some properties here, and if you kind of flash back to the properties we already have for limits, you're going to see they are practically identical. All right, and the reason for that is that our definition of continuity is based on a limit. So a lot of those properties are going to kind of naturally carry over. For example, I'm not going to belabor all of these, but just look at the first one. If f and g are continuous at a point C, then their sum is continuous at that point. Okay, well, think about our three criteria for determining if a function is continuous at a point. First, is a function defined there. Well, if f is defined at C and g is defined at C, then f plus g is going to be defined at C. And we want to talk about the limit as x approaches C of f plus g. Well, our limit properties say I can split this up to the limit as x approaches C of f plus the limit as x approaches C of g. But because we're assuming f and g are continuous, these limits must exist. And each limit, the first one is f of c, and the second one is g of c. And this is just f plus g of c, right? So all of these follow in a very similar way, just kind of playing off of the corresponding limit properties. One thing I want to point out, I'm looking ahead a little bit, you'll notice that function composition is not mentioned here. Function composition is actually a little more complicated, and we're going to talk about that near the end of the lecture. Okay, so first, and I know I just rattled these off on the last slide, but I wanted to put these up here because we're going to use them over and over again, looking at the examples on the following slides. We've defined a function to be continuous if and only if all three of these properties are true. First, f is defined at C, the limit as x approaches C of f of x exists, and that limit equals f of c. All right, so let's look at some examples. First, all polynomials are continuous, right? And again, we're going to get this from a very similar thing that we showed when we were talking about limits of polynomials, right? We saw that the limit as x approaches c of p of x, where p of x is a polynomial, equals p of c. And that's just our continuity criteria, right? First, we know that the domain of all polynomial functions is all real numbers. So we know that p is going to be defined at C. And this property that we showed back when we were first talking about limits shows first that the limit exists, and second that it equals p of c, which is all we needed, right? All three of our properties are satisfied. Okay, so how about this one, right? 1 over x minus 1. And I want to look at them visually, right? Because looking at the graph, a lot of times they're going to point us in the direction of how to answer these questions about continuity. So you know, hopefully, this function has a horizontal asymptote at x equals 0, and a vertical asymptote at x equals 1. That's the point where the denominator equals 0. So the graph looks like this. I want to talk about continuity. Well, sometimes it's easier to talk about discontinuity. This function is discontinuous at x equals 1, at this asymptote here. Right? And to see why, refer back to our three criteria. Right? Criteria first, c is equal to 1 here. Right? I'm talking about where x equals 1. Look at the first criterion. Is f of c, is f of 1 defined. Well, no, it isn't. The function is undefined at x equals 1, and that's enough. Right? Therefore, the function is discontinuous there. So how would we say this? Well, I can put this one of two ways. I can say f of x is discontinuous at x equals 1. And if I had to give a reason, I would say because it isn't defined there. Or you can go the other way, and you can say f of x is continuous everywhere else. So I'm going to say on negative infinity up to 1, union 1 up to plus infinity. Which way is correct? Well, they both mean the same thing, right? But when you're doing this like on a test or something, you always have to be mindful of that. When you're answering a question like this on a test, just be mindful of what the question is asking for. Right? If the question said, where is the function discontinuous, then you're going to go with this version. If it said, where is the function continuous, then you'll go with this one. Okay, so how about this thing? Right, f of x equals the square root of x. Well, again, it helps to go to the graph. The graph looks like this. And so it's not defined for negative values of x. Okay, so the point that I need to be concerned about here is 0. Okay, the function is discontinuous on negative infinity up to 0. And I'm going to go with the open interval here. It's discontinuous on that interval because it's not defined there. Right? And the function can't be continuous in places where it isn't defined. So how about 0? Well, at 0, we have a potential issue with number 2 here. The limit of f of x as x approaches 0 does not exist. Because the limit from the right exists. The limit from the right is 0. The limit from the left does not exist because the function isn't defined on that side. But if you remember how we define continuity on a closed interval, then we said a function is continuous on a closed interval if it's kind of a regular continuous on the interior. And in this case, because 0 was on the left-hand side, we would also say it's continuous if it is left continuous. Excuse me, wrong side, right continuous. If it's right continuous to 0, and it is right continuous, because over here on the right-hand side, the function is perfectly well behaved. Okay, so I would say this function is discontinuous, just where I said it was, negative infinity to 0. And I would say it's continuous on the interval from 0 up to plus infinity. Right, so remember, that's why we defined left and right continuity, was because this function really is well behaved at 0. It's not doing anything bizarre there. Right, so we did want to include this kind of closed interval in our definition of continuity. Okay, so how about this thing? How about this? Well, and again, it's informative to graph it, I think. Notice how these x minus 1s, they kind of cancel out, right? So when x is not equal to 1, the function is the same as x plus 1. Right, we just watch. It's got a y-intercept of 1 and a slope of 1, so it's going to go kind of like this. And then this line part of the graph, it doesn't apply at 1. So when I get to 1, I got to put a circle here, right, to not include that point. What do we know? At 3, at 1, I'm going to somewhat arbitrarily define the function to be equal to 3. So that's up here. Okay, and I want to talk about continuity of this thing. So where is this function discontinuous? I'm going to make the argument it's discontinuous at 1, right? But why? So let's go to our definitions here. F of 1 is defined. Yes, it is. F of 1 equals 3. So yes, the function is defined at 1. Does the limit as x approaches 1 exist? The limit x approaches 1 of f of x. Well, yeah, it does. It equals 2. Right? It equals, it's coming From the left, it's coming this way. From the right, it's coming this way. Yeah, that limit does exist. However, number 3 is where we're going to run into trouble. F of 1 is 3, which does not equal that limit. Therefore, the function is discontinuous. Let me write it. F of x is discontinuous at x equals 1 because the limit of f of x as x approaches 1 does not equal f of 1. That's kind of the language I would use, right? Notice how I'm explicitly referencing which of my 3 criteria was not satisfied by the function. Okay, so how about this one? F of x equals the absolute value of x. All right, well, that one, you remember this has this kind of a V shape. So, I mean, it's outside of 0. 0 is the point where I'm thinking maybe things are going to get a little weird. Outside of 0, it's a perfectly well-behaved line. Lines are polynomials, and we saw earlier polynomials are continuous everywhere. So I know this function is continuous everywhere except possibly 0. 0 I got to take a closer look at. All right, is the function defined at 0? Well, yeah. F of 0 equals the absolute value of 0, which is 0. Excellent. Does the limit as x approaches c of f of x exist? Well, yeah. It comes in from the left or from the right. It's closing in on this point. If it comes in from the left, it's closing in on this point. Yes, the limit does exist. What is the limit? Well, what is that point they're coming into? The limit x approaches 1 of f of x is equal, not 1, we're talking about 0 here. Right, the limit as x approaches 0 of f of x equals the absolute value of 0, which is f of 0. So this function is continuous at 0. Right? In fact, my final answer here would be either this function is continuous everywhere, it's continuous for all numbers, or it is discontinuous nowhere, again, depending on exactly what question you were asked. So this is what a continuous, and I picked this for a reason, this is what a continuous function looks like when we try to apply our 3 criteria to it.
Okay, so where are we going next? Well, we have a couple of theorems related to continuity that you need to be aware of. One is that theorem about composite functions that I mentioned earlier, and another one is something called the intermediate value theorem. If you're not following along with the theoretical, the proof side of this, that's fine. I would encourage you to take a look at that lecture, even if you just kind of listen to my comments on the theorems themselves, especially the intermediate value theorem, because we're going to come back to that one several lectures down the line. As a really great tool to help us find the approximate roots of functions when we find ourselves in situations where we can't find them exactly.